Good morning, grade 11 physics class. It's Tuesday, April 21st. Hope you had a good weekend and you've been able to work on the review that I gave you. I've had a few questions come in and that's great. It shows me that some of you are working on it and getting ready for the test, which will be out on Wednesday. As we get started today, I want to share with you again a verse of the day to encourage you as we start our day off today. Last week I was reading in Psalms, I was continuing to read in Psalms. So last week I mentioned in Psalm 31 there was a but statement that followed, and the but followed with an encouragement. And today again I was reading in Psalm 32, and there's a but in Psalm 32 as well. And Psalm 32 is all about forgiveness and knowing that our sins are forgiven. And in Psalm 32 verses 10 and 11 it says the following: "Many are the woes of the wicked, but the Lord's unfailing love surrounds those who trust in him. Rejoice in the Lord and be glad, you righteous. Sing, all you who are upright in heart." So today we can rejoice in the fact, the knowledge, and the truth that we are forgiven and that we have a Savior in Jesus Christ. So let that encourage you as you go through today. All right. We're going to go through a couple of questions that were asked. So we're going to start with question number 13. So question number 13 on the paper talks about two charged particles that have a force of attraction between them of 1.6 times 10 to the negative 2 newtons. So it's giving us a force. We have two charged particles. Let's see if I can grab two things here. Here's a charged particle. Here's a charged particle. Okay, we have two charged particles. They are a certain distance apart. We don't know what distance that is, but we know that there's a force between them. Okay, so it's the force of attraction because it says they're oppositely charged particles. Okay, so we have a force between these two charged particles. Then it says, what does the force become? So we already have a force. We want to know what it becomes if we do a couple of things. And the first thing we're going to do is we're going to take each of the charged particles and we're going to touch it with a neutral mate and then take that neutral mate far away. Okay, when we first learned about charged particles, we realized that if we have a charged particle and we have a neutral particle, when we touch them together, the charges will spread out. And when we take it apart, this charge and this charge will now have the same charge. So this was previously uncharged. Touch, bring them apart, now they have the same charge, which means that this charge that's left has half of its charge left. All right, so if it was 2, bring in one was 0, now they each have 1, we take that far away, so now this one has a charge of 1. Okay, now we have 2 of those happening, right? It's happening on both sides. So both of these charges are becoming half of what they previously were. So what that looks like is we look at proportionalities, okay? Because we don't have an equation here, we have a proportion. We're looking at what happens when we half something. And we remember that our proportionality statement for charged particles is F is proportional to the charges and inversely proportional to the distance between them. And again, when it's proportional, whatever happens here happens to the force. So if I double the charge, I double the force. If I half the charge, I half the force. Okay? Now, we're doing half of both of these, right? So Q1 is becoming half of what it was, and Q2 is becoming half of what it was. So we're just going to leave it like that for now. We're going to write it like that. It also says in the question that the distance is becoming twice as far, right? We're taking these two that were here, and we're moving them to here, twice as far apart. And so our distance is becoming double. Okay, so instead of d, I'm going to put 2d into here. Okay, so I've got a half of Q1, a half of Q2, and I've got a double distance being squared because our distance was squared in the proportionality statement. All right, I'm going to pull all the numbers out front because again, in math, multiplication, the order doesn't matter. So I'm just going to pull the numbers out front. A half times a half is a quarter. And when I remove these brackets, the 2 becomes 2 squared, and the d is still d squared. All right, now I have a quarter divided by 4, which is 1/16. And just bring the numbers out front. Okay, because again, order doesn't matter. Now, what that means is that here's my Q1, Q2, d squared that I originally had when I first wrote down the proportionality statement. But now I have this factor of 1/16 out front. So that means the answer to our question is, what does the force become? Is it becomes 1/16 of what it was. The question tells us what it was. The question tells us the force was 1.6 times 10 to the negative 2 newtons. By halving each of the charges and doubling the distance, it's going to become 1/16 of that. So we take our 1.6 times 10 to the negative 2, we multiply it by 1/16, and we get 1 times 10 to the negative 3 newtons, which is the answer. All right. So again, and you can do this in pieces. I've done it all in one section, but you can do this in pieces, right? You can take this 1.6 times 10 to the negative 2, you can divide it by 2, and then you can divide it by 2, and then you can multiply it by 4, right? That would be doing it in separate stages, which is totally fine, or you can do it like I've done it here, put the numbers into the proportionality statement, bring the numbers out front, giving us a multiplication factor, which then we can make our change. Either way works fine, but because they're not giving us numbers, they're just asking us what would happen. That's your cue that it's a proportionality statement and that we're looking at factors of proportionality. Whereas if we half a charge, we half the force. Okay, hope that makes sense. Let's go do question 14 on the other board here. Question 14 tells us, it's asking us for what is the difference between two protons if there's a force of 4 times 10 to the negative 11 neutrons. All right, so now this question is an equation question. This is using our force equation, Coulomb's law, which is F equals K, Q1, Q2 over D squared. Okay, that's Coulomb's law, that's our equation for when we have the numbers of force and charge, right? This question is giving us a force, and it's giving us the two charges and asking us to find the distance. So we just need to take this formula, plug those numbers in. Okay, the force was 4 times 10 to the negative 11 newtons. K is 9 times 10 to the 9. Remember that number, because you'll need it for your test. The charge on a proton is given in the question, and it's a number that we'll use over and over and over again. 1.6 times 10 to the negative 19 coulombs, and then it's times itself again, right? Q1 and Q2, but they're the same, so I just wrote it as squared over D squared, and now we want to solve for D. And so to solve for D, we're going to basically, in the end, we're going to switch these two positions by multiplying D squared on both sides, dividing by the 4 times 10 to the negative 11. End result is they switch places. Take the square root of both sides, and we are left with this answer here of 2.4 times 10 to the negative 9 meters. All right, so again, this is just, putting numbers into a formula, rearranging and solving for the variable, and I hope you can all do that. All right, the other question that was asking me to go over was both question 22s, question 22 on the first page and question 22 on the second page. Question 22 on the first page I can deal with verbally. I forgot to include the diagram for that question. So you can omit that question as there is no diagram for it, and you have enough other questions of that type that it's fine if you omit that question. Question 22 on the second page we'll do on the other board. All right, here's question 22. Question 22 says we have a conductor with a length of 40 centimeters, has a mass of 15 grams, and it lies in a horizontal position at a 90-degree angle to the field lines of a horizontal magnetic field of 0.2 teslas. What must the current in the conductor be so that the magnetic force on it will support its own weight? All right, so what we're given here is we're given this information. We've got a length, we've got a mass, we've got a magnetic field, and we want to find the current. And so we will be using our formula F equals BIL. You'll notice I did not write the sine theta. It was told in the question that theta was 90 degrees, so sine theta is 1. I'm not going to write it down. Now, the question says, what must the force be in order for it to support its own weight? So we want to find I so that we get a force here that supports its own weight. Now, to support its own weight, if it's up here, there's something pulling it down, right? The force of gravity is pulling it down. We want the magnetic force to hold it up, right? And so in order to suspend something like this in air, the force, upward force, this magnetic force, has to be equal to the gravitational force pulling it down. They have to be equal and opposite. If it's not equal and opposite, it's going to move up or it's going to move down. We want them to be equal and opposite. So that means this force, this magnetic force, has to be equal to the force of gravity on the wire. Force of gravity can be found because we have a mass. Remember that the force of gravity, so this must equal Fg. Well, Fg is mass times the gravitational field constant, and BIL. We can plug in our numbers, 0.015 kilograms 9.8 newtons per kilogram equals B, 0.2 Teslas times I times 0.4 meters. And if we have this, I'm confident that you could solve for I, and if you do so, you will get I equals to 1.8 amps. And the trick to this question is recognizing that in order to support its own weight, it has to overcome the force of gravity on it, which means to just be static in air, it has to be equal to the force of gravity, and so that gives us this equation here, that the force of gravity equals the magnetic force, and then we have enough information to solve it. All right, I have one other question about the direction on question number 23. So question number 23 says, what is the magnitude and direction of the force on an electron moving horizontally to the west through a uniform magnetic field pointing horizontally to the south? All right, so we want to find force. Now again, force is the palm of our hand. In this case, it has to be the back of our hand because it's an electron. And so when we get to the end, when we look at find the direction of force, we'll be looking at the back of where the back of our hand is pushing. So its velocity is moving to the west, so we need our thumb pointing to the west. So if north is in front of us, west is left. So I'm going to put my thumb to the left. That's our starting point. The magnetic field is our extended fingers. The magnetic field is pointing to the south. So I need the fingers pointing towards me. How can I do this? I'm going to do it this way. Okay, my thumb is still pointing to the left. My fingers are pointing towards me, which means that the back of my hand, because it's an electron, the back of my hand is pushing down. All right, and so that is the direction down. So again, remembering that the thumb is the velocity, the fingers are the magnetic field, the force is either the palm or the back of the hand, depending on what kind of charged particle it is. It's the palm if it's a positively charged particle, it's the back of the hand if it's a negatively charged particle. So west, south, back of the hand is pointing down. Hope that makes sense. If you have any other questions, ask away and I will try to answer them as best I can. On Wednesday, your test will go up on Connect and you'll have a few days to write it, complete it, and get it back to me. Hope you have a great day. We'll see you tomorrow.